Good morning, everyone. My name is Shulin, and I will be today's host for the webinar. And thank you all for joining us today. Mr. Li Junnan, who is a lead research scientist at Salesforce Research Asia, will give a talk about representation learning without human annotation. Mr. Li Junnan obtained his PhD at National University of Singapore in 2019. He has published in many top-tier venues in machine learning and computer vision, such as NIPS, ICLR, CVPR, ICCV, etc. His main research interests include vision and language, self-supervised, semi-supervised, weakly supervised learning. His ultimate research goal is to build general-purpose AI models that can self-learn without human involvement. Representation learning has been the key factor of success for many deep learning models. While conventional representation learning relies on a larger amount of human annotated data, learning without human annotation has become the modern trend. This talk will introduce several key directions to advance representation learning with few human annotations, namely self-supervised learning, semi-supervised learning, and weakly supervised vision language pre-training, as mentioned before. The talk will focus on state-of-the-art methods in recent developments. Now, please allow me to pass my time to Junnan. Junnan, please.
Thanks for the nice introduction, and happy to share my work here. Shall I share my screen or do you use your slides?
Yes, please share your screen. Yeah, thank you.
Okay, can you see my slides?
Yes, we can see.
Yeah, great. Yeah, so hi everyone. Thanks for joining at such an early morning. Today's topic is representation learning with few human annotations. And my name is Junnan from Salesforce Research Asia, based in Singapore. So what is representation learning? Let's take computer vision as an example. So given an image, we will pass it through some model, which is usually a neural network, to obtain a feature vector. And we hope that images with similar semantic meaning will also have similar limitations. And images with different meanings should have different limitations. In essence, we want these limitations to capture the class information of the image while discarding some irrelevant information. So let's say we also have some data from a different modality. For example, text here, a cat is lying on a blanket and holding a keyboard. We also want the representation of the image to be similar on this textual description. So if we put it in one sentence, representation learning aims to learn a summary of data, which preserves the important information. And this importance is defined with respect to the downstream task. For example, here, for image classification tasks, we only care about the class information. So there are three main paradigms of representation learning. The first one is supervised learning, which is the conventional approach, where the model is given access to both images and the labels. This type of learning will have a clear optimization objective, which is to optimize the cross entropy loss with respect to the ground truth label. But this type of learning is quite expensive because it requires a high quality human annotation. The second paradigm is semi-supervised or self-supervised learning, which utilize a large amount of unlabeled data. This is much more scalable, but the problem is that there's no clear optimization objective. So people need to come up with their own task to perform this unsupervised learning. And the third paradigm is webly-supervised visual learning, which make use of a large amount of freely available text on the internet that comes with the images. But there's a potential misalignment between the image and text. For example, here, right, my cat is learning to type so funny. It's correct, but it's not 100% describing the visual content of the image. And we will see some examples later on how to deal with this problem. So in this talk, I will mostly focus on self-supervised, semi-supervised learning, and visual language learning. Here's a quick look of what we have today. I will talk about 4 papers that we have published in my group. The first paper is about self-supervised learning, and the title is Prototypical Contrastive Learning of Unsupervised Annotations. So first, let me quote from Yan Kun, who believes that unsupervised learning is the foundation of this cake of modern deep learning. And indeed, unsupervised learning has become a very important topic in recent years. So here is a brief summary of the history of self-supervised learning. So before 2019, which we can consider as the ancient time of self-supervised learning, people have tried to invent different pretext tasks, which are quite heuristic, such as to predict the rotation of the image. And then there comes contrastive learning, which is a game-changing method that makes self-supervised learning very effective. And in the meantime, there are some other approaches that explore clustering. And I will introduce our PCL paper, which bridges contrastive learning and clustering. And very recently, there has been a new trend called mask image modeling, represented by this BATE and MAE, but we will not cover this topic in today's talk. So how does contrastive learning work? In contrastive learning, we are given an image, a labeled image, and we use data annotation to generate 2 views of same sample. And we feed those 2 views into an image encoder to get this permutation vector V. And we enforce this info NCE loss, which basically encourage the similarity between permutation from the same image to be higher compared to similarity of the permutations from different images. For example, shown here, right, we have the same image and their embeddings are put closer, but for different images, their embeddings are pushed away. And this task is also known as instance discrimination task. So there is a clear limitation of this task. In particular, because we don't have any class information, those are all unlabeled images. We can accidentally make images from the same class to have different features because they are considered as this different instances. So in this paper, we propose prototypical contrastive learning, which bridges contrastive learning and clustering. Sorry, just give me a minute. Sorry, just 1 minute. I need to take an urgent call.
Hey guys, if you have some questions, feel free to type in your questions in the Q&A session. And if you want to open your mic, we will have a Q&A session after Mr. Li Junnan's talk over. Yeah.
Okay, I'm back. Sorry about this. Okay, let us continue. So in our prototypical contrasted learning, we will do clustering on the unlabeled images. And we call the cluster centroid as prototypes. And we assign each image to multiple prototypes of different granularity. And we train the model with objective to pull each image embedding closer to its associated prototypes. And we formulate PCL as an explanation maximization problem. Basically, our optimization objective is to maximize the log likelihood of all the observed unlabeled samples. And we introduce these prototypes C as the latent variable. And our algorithm is a two-step procedure. In the first step, which is an E step, we will do clustering to estimate the probability of these prototypes. So here we do a simple k-means clustering where it will return us a set of deterministic cluster centroid as our prototypes. And in the second step, which is the M step, we will use these prototypes that we have obtained to optimize the model's parameter by doing this maximizing this lower bound of the log likelihood function, which we can derive as this equation here. So here, V is the feature for a particular image, and C is this CS is its associated prototype, and the CJ is all the prototypes. So by optimizing this, we essentially will pull the image closer to the prototype that it is belongs to. And we also introduce this concentration of each prototype, which we can dynamically estimate based on some statistic of the clusters. So if you look at this equation and you compare it with the previously shown info NCE loss, we can see that our PCL loss is actually a generic form of info NCE. If you just replace this prototype with the feature of the same instance, you basically get the same equation as the previous loss. Our formulation here is a more general way of performing this unsupervised contrasted learning. And in practice, because we don't know the ground truth of these class labels or the clusters, what we can do is we can perform multiple rounds of k-means clustering to obtain different clusters for each image. And we assign each image to multiple cluster centroid, and we can jointly optimize this loss for all the clusters. And this is our final formulation. So here is the experiment. So how do people generate the self-supervised learning is by transferring the model to different downstream tasks. For example, here we transfer it to the VOC dataset and the places dataset, which are object and scene recognition datasets. And we will freeze the pre-trained model. So we pre-train this model on ImageNet first using unlabeled images, and then we freeze the entire model. And we only train a SVM, a linear classifier, on top of the frozen features. And here the K in the table basically means how many labeled samples we have on this downstream data set, which is a low shot image classification scenario. And if we compare with this MoCo from Facebook and Sinclair from Google, you can see that our method can outperform those methods on this downstream task. And we also perform experiment where we fine-tune the pre-trained model. So here we allow the pre-trained model to be fine-tuned on the downstream task using label data. And we experiment with both 1% of label data from ImageNet and 10% from ImageNet. And again, in this scenario, PCL obtain much better performance than some existing works. But note that because our paper was published more than a year ago, so there, of course, was some recent paper that can outperform PCL. And finally, I will show the downstream task of object detection. Again, we will fine-tune the pre-trained model on the VOC detection dataset, where we can again get better performance. And lastly, because we introduced this class string objective during training, we can directly compare the quality of the clusters with respect to some previous method. And this AMI is basically a metric that measures how good are the clusters. And here I also show some visualization of the images embeddings obtained by MoCo or by PCL. And this is ImageNet features. You can see that because of this explicit objective of PCL to pull the samples closer to its associated prototype, what we get is more clearly defined boundaries between different clusters. Okay, this is all for the first paper. So do I do the QA now or after I finish everything? I think better to take some questions if the audience have any before I proceed.
Sure.
Yeah, any questions? Okay, if no, I will just go on. Okay, so the second paper I'll talk about is this co-match, which is a semi-supervised learning work. So what is different from self-supervised learning compared to semi-supervised learning? The only difference is that now we not only have a large amount of unlabeled data, but we also have a small amount of labeled data. And we can use this to train our model. So the question is, of course, how to make use of unlabeled data, given that now we have some labeled data. So there are two approaches of learning from unlabeled data. And maybe I'll introduce a second one, which was this contrast learning that I have just talked about. We have the same image and we perform different augmentation, and we enforce that the same image with different augmentation should have similar features in contrast to other images. And this again have the limitation that images from the same class will have different limitations, and this is undesirable for classification tasks. And there's another approach which people call it the self-training or pseudo-labeling. And the method is quite simple. Basically, you can use the model you have to predict labels for the images. And these labels are just class probabilities that are produced by your classifier. And this is the so-called pseudo labels that you can use as target to train your model. And you can clearly see that there's an issue with using yourself to train yourself, which is called confirmation bias, because the pseudo labels could be noisy and the errors would accumulate and your model cannot recover from such mistakes. Okay, so then in our paper, right, we take a new approach to address these limitations. Basically, in co-match, we will jointly learn both the class probabilities and the image embeddings in a co-training framework. So given an image, we have this CNN backbone. And this CNN backbone will produce a feature. And this feature will be given to two heads. One is a classification head that can produce the class prediction. And the other is a projection head, which can produce the embeddings of the image. And those two heads will interact with each other during training. Specifically, we use the embeddings, the yellow color feature here, right, to impose a smoothness constraint on the classifier that we can improve the pseudo labels. And then we also use the pseudo labels as additional information that we can use to train the this embedding layer with a graph-based contrastive loss. Next, I'll explain in more details what I mean by this smoothing and this contrastive loss. But this is a high-level overview of our method. So first, how do we use the embeddings to improve the pseudo labels, right? So given an image, we can get the prediction P and the embedding Z for each image. And we also keep a memory that stores the embeddings and the pseudo labels for the past samples. Right? And given a new sample, we impose this smoothness constraint, which basically says that this new sample should have a similar pseudo label with its neighbors in the memory. So let's say there are, it has 5 neighbors in the memory, and those neighbors are all dogs. Right? And then we say that, okay, this new image should also be a dog or something similar to a dog. So this is what we mean by smoothness constraint. And we also have a prediction constraint, which basically says that the final pseudo label Q should be close to its model's own prediction. So this is quite straightforward. And if we optimize this objective, what we have is basically this weighted combination. So Q is the final pseudo label, P is the model's prediction for this image, and the second term is a weighted average for all the neighbors in this memory bank. And by doing this, we are kind of taking account into the structural information of the data set to improve the pseudo label of this individual sample. So this is how we get Q, the pseudo label. And we can use this pseudo label to optimize this cross entropy loss, where we treat it as a target, and we train the model to predict this target given this sample. Okay. And the second objective is this graph-based contrastive learning, which is how we use the pseudo labels to improve the embeddings. Right? So in the previous slides, what we show is how we use the embeddings Z to improve Q. And next, I will show how to use Q to improve Z. So let's say we have a batch of images, right? We can construct this pseudo label graph, which basically says that if 2 images in the same batch have a similar pseudo label, we will add the edge between those 2. This is a pairwise graph. And if 2 samples are not similar, then there is no connection between those 2. And similarly, we can construct this embedding graph. And this embedding graph is the same as the pseudo label graph, except that now we use the embeddings Z to construct this similarity. And then we enforce the loss that makes the embedding graph to have the similar structure as the pseudo-label graph, which basically says if two images are similar in the pseudo-label space, it should also have a similar embeddings. And I will not go into details into the equations, but from high-level perspective, our loss is just a cross entropy loss between the normalized pseudo-label graph and the normalized embedding graph. So during training, we jointly optimize those losses together, and I'll jump to the result here. So for semi-supervised learning, we are given a small amount of labeled samples and a large amount of unlabeled samples. So here we have a different label available on CFAR10, and across all the settings, we can outperform the state-of-the-art method, fixed match, which was developed by Google. And the same on ImageNet, where we perform this experiment with either 10% of labels or 1% of labels, and we can observe quite a big improvement compared to fixed match. And we also experiment with using self-supervised pre-training before we do this semi-supervised learning. Specifically, we can take the unlabeled image first and do self-supervised learning, right? And then we can use the labeled image to do a second step. The second step can be either fine-tuning using only the labeled images or doing this semi-supervised learning with unlabeled images together. Right? And again, with this pre-training step, we can observe an improvement in the performance, but co-match is still much better than the other method. So here we also include the performance of PCL followed by fine-tuning, which was not as good as co-match. So here I show some illustrations to just to demonstrate why co-match have better performance. So here I show three figures. The x-axis are epoch, the training epoch. And the first figure shows that co-match produce better accuracy in the pseudo labels. And because the pseudo labels are more accurate, of course, there's more there's better supervision signal provided by the pseudo labels. And not only they are more accurate, they are more confident as well. Right? So because more confident pseudo labels is also better because they give us more useful samples. So again, co-match is more confident. And the third is just the text accuracy, right, during training. And we can see that from the beginning, co-match is better than others. And this advantage will maintain as the training proceeds. And lastly, I'll show that we can actually transfer this model learned by co-match to downstream tasks. So here we tested on this VOC data set again, which is a low shot classification. And if we compare with MOCO or SWAL, which are the state-of-the-art self-supervised method, we can see that using label data with co-match enables better repetition learning for this transfer. Okay, so that's all about the second work on semi-supervised learning. Any questions? Just to make sure, is everyone following or any feedback from the audience? Because I cannot see anything. Because this is a tutorial session, I think it's better to keep it interactive. Can the audience type in the chat if they have any questions?
Yes, for the audience, feel free to use the Q&A function in the bar below so that you can type in any questions that you are interested in. Thank you.
And let me know if I need to slow down or there's anything unclear. I can go back. Okay, I guess no questions. Okay, and then I'll proceed to the next topic. So the next topic is this vision language learning, where we are given this web text together with the images. So here I'll introduce two works published by our group. One is Aneurysms, and the other is CVPR this year. So the first work is titled Align Before Fields, Vision and Language Representation Learning with Momentum Distillation. So what is vision and language pre-training? This vision and language pre-training aims to make use of images and the alt text pairs that are freely available. Okay, I think I got one question. Sorry, I missed it in the QA. But I'll answer it first before I proceed. Will co-match be faster in training since it requires less label data? That's a very good question. So it depends on what you compare with. If you compare with the unlabeled, the self-supervised learning is actually faster in terms of it requires less epoch to converge. And the reason is because it uses a small amount of label data to help it learn faster. If you compare with supervised, fully supervised learning, right, it's not faster because even though it have less label data, it still use unlabeled data. And the total amount of data is the same. Given that condition, supervised learning will converge faster compared to semi-supervised learning. So more labeled information always helps, but the problem is we don't really have that, and it's expensive to get labels. Okay, hope that answers your question. Yeah, let me proceed with this vision language pre-training task. So yeah, so for this vision language pre-training, right, we have this multi model data, and we can train this multi model that can understand both image and the text and perform different tasks such as retrieval, multi-model classification, visual question answering, or phrase localization, etc. So let me introduce the background of existing works in this field. So for existing vision language pre-training methods, people usually will use an object detector to extract image features, and they will use this word embedder to extract the word features. And they will concatenate those features and give it to a multi-model encoder, which is usually a transformer architecture. And then people will commonly use these two laws to train the model: image text matching, which is a classification laws to tell whether this image and text is matched or not matched. And the other laws is this mask image modeling, which is commonly used in NLP, where you basically mask certain words and you try to predict the mask token. So there are several limitations for this kind of architecture. The first limitation is that the image feature and the text features, they are not aligned before they are given to this multi-model transformer. The reason is that they have not seen each other before, and they are extracted from different models. So they are in completely different feature space. And this makes it difficult for the multi-model transformer to fully understand what is the meaning and the interaction between those two different types of data. And the second limitation is from this object detector. This object detector is usually pre-trained on some other data set using human-annotated bounding boxes. And this is expensive during training. And also it's expensive during inference because the object detector requires large resolution of images. And furthermore, the detector is limited in the number of categories it can detect. if you use MS COCO dataset to train your detector, you only have 80 classes, and you cannot detect concepts such as the sunny day. And the third limitation is that this overfitting to the text that are quite noisy. Remember that those texts are collected on the web automatically. So there could be some words that doesn't correspond to the image. For example, here we have this near my apartment phrase, which was not in the image. But if you try to predict the sentence using the image, you are not making use of the visual information. And this will make your model to overfit to the text. So how do we address those three limitations? We introduce this align before fuse architecture, LBAF for short. In LBAF, we have three models. We have this image encoder to encode the image into a sequence of features. And we use a vision transformer here, but you can also use others such as a CNN architecture. And we have this text encoder to encode the text information. We use the first 6 layers of this BERT model as our text encoder, which will also give a sequence of features for your sentence. And then we have this multi-model encoder, which will take into account the information from the image using cross-attention layers. So for this, we will basically take the last 6 layers of the BERT pre-trained model, and we add this cross-attention as additional module to incorporate the image information. So in LBAF, we will jointly optimize 3 training objectives. The first objective is this image text contrastive learning. It's similar to the contrastive learning we introduced earlier, but here is cross model, meaning that we use a feature from image and we use another feature from text, and we encourage those features to be similar. So this objective basically aligns the unimodal features, right? So it makes the image and text feature to reside in a similar space. And this will make it much easier for the multimodal encoder to understand the interactions between those two modalities. Our second training objective is this image text matching loss. And this loss aims to learn the multimodal encoder, right, the last part, including the cross-attention layer. So it is applied to the output of the multimodal encoder. It is a classification task, a binary classification task that tells whether an image and text pair is positive, meaning that they are matched, or negative, meaning that they are not matched. And because these negative pairs are randomly combined based on your data, it could be quite easy a lot of times to tell that this is not a matched pair. So what we do is we use this contrastive loss to do a hard negative mining, where we will construct negative pairs that are actually more similar, but they are not the same. So by doing this, we get more informative negatives that helps us to learn a better model. And our final loss is this mass language modeling loss, where we predict the word based on the image and the contextual text. Okay, I get a question. Thanks for the question. So what is the reason for using the first layers of BERT as text encoder and the last 6 layers as a multimodal transformer? Yeah, I think you pretty much answered it very well. So the reason is we want to take full advantage of the pre-trained weight from BERT. So we want to keep minimum change to BERT because original BERT have 12 layers, right? So we just maintain its original first layer to encode the text, and we just insert this additional module, the cross-attention module, into the last six layers, so that we are not disrupting the knowledge from the pre-trained bird. We are just trying to add new knowledge from this image modality. Yeah. So I hope that answers your question. Yeah. So we are instead of pre-training everything from scratch, we think we observe that this is a much better solution, given that we don't have a compute to pre-train bird from scratch. And actually, this paradigm has been there are some recent follow-up work from Google that also use this kind of cross-attention into a language model to incorporate the image information. Okay, so recall that we have another problem, right? Is that those texts are quite noisy. So if you have a text that is not matched to an image, but you try to predict it as matched, right? Then it will cause a problem. So here, how do we address this issue is that we will maintain this momentum model, which is a continuously evolving teacher. You can consider it as a copy of your model, but this copy is a smoother version because the parameters of this momentum model are updated using a exponential moving average instead of just a pure copy. And we will use this momentum model to generate pseudo labels for our ITC, the contrastive loss, and the mass language modeling loss. So I will not talk about how do we do that. I'll just show you some examples to intuitively show why this is important. So here is the mass language modeling task, where we will mask some word in the sentence and try to predict the ground truth token. And here we show 5 images and the corresponding ground truth word. And also we show the top 5 pseudo targets produced by this momentum model. And you can see that, of course, the ground truth sometimes will still make a lot of sense. So the first row is for the mass language modeling, and the second row is for the contrastive learning. Let's talk about the first row first. So the ground truth, for example, in the first image is wild, right? A polar bear in the wild. Maybe not 100% what you would want to say, so that the pseudo label will actually produce something like zoo, pool, water, pond, and only the 5th option is wild. And this actually provides us with a lot of useful supervision that help us to further benefit the model training. And the similar situation for the contrastive objective. We have a ground truth sentence that is paired with the image breakdown of the car on the road. It's good enough, but if you look at the pseudo labels, the top 1 sentence, and this is basically retrieved from the data set, right? This is not generated, but this is another sentence from the data set. And this sentence is young woman get out of the car near the road, which I would say also describes the image quite well. It contains this concept of young woman, which doesn't appear in the original ground truth. So this is how the pseudo label from the momentum distillation can bring advantage to the model. So after the pre-training, we will take this pre-trained model to evaluate on some downstream tasks. So here we have this first task as image text retrieval task. The goal is to get the text corresponding to the image and vice versa. If you look at the evaluation, our LBAF is much better than previous work in terms of the recall for both Flickr and MS Coco, those 2 datasets. And this Align is a paper from Google that actually used 1.2 billion images for pre-training, but we only use 40 million, which is 100 times smaller. And we also perform this downstream task of visual question answering, where we try to predict an answer given the image and the question. And again, compared to the SOTA method, LBAF is much better in terms of the answer accuracy. There are some other tasks in the paper, but I will not show all of them. I will show this one that is quite interesting. And actually, we are surprising to discover this capability. So basically, we can use LBAF to localize the important region in the image that corresponds to a certain textual description. And we do it by using this GradCam, which is a visualization technique. And we put it on the cross-attention map. We call that we have this cross-attention from the image encoder to the text encoder. So if we visualize the GradCam, you can see that it can accurately localize where is the text, right, inside the image. And we can also do localization for answers, not only for phrases. We can also visualize the answer corresponding to a question, right? You can find the chopstick for this answer chopstick. And it can also do per word localization, where if you localize a cross-attention map for each individual token, we can get the localization for each word. Even for the action holding, we can localize where it happens. And this was quite impressive that we discovered that wasn't able to be achieved by any previous models. Okay, so that's all about the vision language paper LBAF. Next, I will maybe just quickly talk about this our CVPR paper, which is align and prompt. And this is in video domain, not in the image domain. And the novelty is that we introduced this new method called entity prompt. So for video and language pre-training, it's similar to image, except now we need to use a video encoder to encode the visual information instead of the static image encoder. So again, there are some certain limitations, right? In particular, we don't have a counterpart for the mass language modeling loss on the visual information. So let's say we mask out certain region from the video. Can we let the model predict what is this region? Right? And if we can do so, then there's a lot of useful supervision signal we can obtain by doing this. But the question is, how can we know, given that we don't have any annotation, how do we obtain the label or the pseudo label for specific regions in the video? Of course, we can use object detector, but there's a limitation, right? There's a limited number of categories, and maybe your detection is not accurate due to this domain shift problem. So what we try to propose is we use this prompter module to find those pseudo labels. So this prompt module basically uses contrast learning to learn the alignment between the video modality and the text modality. And then we construct this prompt, which is basically a template of a sentence followed by a name of the object. And this technique was first proposed by the famous CLIP paper from OpenAI, but here we extend this technique for this video and language pre-training task. So after we get this prompt, we can basically measure the similarity of any video feature to the list of prompt. And this will give us a pseudo label, right? We can change whatever name of the category in the prompt, and we can get a list of similarities for any kind of video region. And this is how we get the pseudo label. And we can ask the model to predict, right? We can mask this patch from the video input and ask the model to predict what is contained in this patch. And we call this task as prompting entity modeling task, as shown here. And we have some of the other tasks, including the contrast loss, as shown before in the LBAF paper. But now we introduce an additional loss here. And to show some examples, right? So because of this prompter module, now we can generate pseudo labels for random regions in a video. For example, we can mask out different regions in the same image, right? Or the same video, and it can give us different pseudo labels. For example, here we mask out this Singapore, this image from Singapore, and if we mask out the bottom region, the pseudo label will be cruise and ship, and if we mask the top region, the pseudo label will be skyscrapers, etc. And again, I'm not going into details about the evaluation, but our model will outperform the existing SOTA by a very large margin, despite using a very few amount of data. So here we only use 5.5 million video for pre-training. And because we have this efficient way of finding extra information from the data, we can get a good improvement. And the same for the VQA task. So that would be the end of the talk today. So we have open source all of the code and the models that for the 4 papers I have discussed about today. So welcome to check it out on our GitHub page. And we have also some recent works in vision language for training that we have open source. Actually, it outperforms our LBAF model. So also welcome to check out. That will be all. Thank you. I'll take some questions if there are any.
Thank you, Junnan, for your awesome talk. Guys, if you have any questions, feel free to put up, and Junnan will be here to answer you. Okay, here I got a question. So do you have any suggestions for our young researchers as a lead research scientist in Salesforce Research Asia?
Yeah, it's quite a broad question.
Yeah.
Yeah, I'm not sure if my experience will be suitable for everyone. So is the audience here, they are all PhDs or?
Some of them are undergraduates, some are masters, because our audience is coming from different degrees. Yeah.
Okay, I see. Yeah, so if you are currently doing research in the deep learning area, I hope you all the best. I understand it's quite challenging and becoming increasingly difficult. Yeah, but I would say as long as you can find a direction that you're interested in, then aim for work that have higher impact. That would be my suggestion. And also, if you're interested in applying for our internship, we are looking for interns in Singapore and also abroad as well. So if you're interested in joining my team, just send me an email. So we are doing this vision language research currently. Yeah.
Thank you. And what do you think is the most exciting and challenging part in the development of representation learning? Yeah, could simply explain.
Yeah, I guess currently the challenge is this industrial labs. They are just scaling up the model and the data, and it's quite effective, honestly. So So I guess the challenge is how can we push for a different direction where we can make more efficient use of data rather than purely doing a brute force way. So that's one of the focus of my team as well.
Sure, thank you. And one last question from me. What is the biggest block that you think is hindering the development of the representation learning?
Sorry, I didn't catch your question.
Yeah, may I explain again? What's the biggest block that you are thinking is hindering the development of the representation learning?
I would say computing resource, especially for a lot of
Deep learning tasks.
university labs. Yeah. It's almost impossible to do a pre-training work if you don't have enough GPUs.
Yeah. For all tasks, it's like so.
Yeah.
Yeah. So is there any other questions from our audience?
Yeah,
Okay.
someone is asking a link to the models. Yeah, let me just send you. So you can go to my personal webpage and you can find those. Let me maybe just send you my website. Yeah. I'll also send this to the chat. Yeah, so this will include the code and the paper for all the work that I've talked about and also some other works.
Okay, well received. Thank you. Okay. Is there any other questions from our audience?
Thank you again for joining the meeting in the morning.
Yeah, we got another questions from the chat. It says if we are looking for the intern or opportunities, will you be open to contact via email?
Yeah, you can send me an email. So in general, we are looking for PhDs, maybe more senior PhD at their third year, but of course, junior PhDs with good research background is also welcome. Currently, we are not looking for master or undergrad, but that might be possible in the future. Yeah, and if you are interested in some other directions, so in Salesforce Research Asia, we also have research team in the AI ops and AI software. So you can also let me know if you're interested in those directions. And also we have this IPP program. I'm not sure if you are aware, for undergrad and masters, if you want to do a PhD and if you are PR, you can apply for this IPP. It's a joint industrial PhD program. The compensation is quite high than normal PhD program. As long as you are PR, you can apply for that program. Okay, guess no more questions. Would that be all for the day?
Okay, if there's no other questions, okay, that's all for today. And thank you, Junnan. Let's thank Mr. Li Junnan again for his awesome talk.